So this is just to recall what what are the concepts that we have learned so far. So if you just recall the Gaussian elimination, Gauss-Jordan form, Gauss-Jordan elimination, then we have also seen the rank of a matrix and linear independence. Then finding the inverse using Gauss-Jordan elimination process. Finally, we have seen that normal forms and the rank. Now, yesterday there was a question that if we have a matrix A, then what we write? In order to find the normal form, we write here for this particular matrix I3, A and I4. And let us write I4 by 4. So if it is I4 means 4 by 4 order identity matrix, and I3 means 3 by 3 order identity matrix. So we the working rule that I have mentioned here, that if we do row operation, then the left hand side matrix will change. Now, okay. So initially I have given the working process. Now Raghuram has asked about the logical reason behind this. Why such event is happening? So for that, let us we have to understand some more operations that initially I have skipped. So I will explain those operations now. So it's called elementary matrices. On definition, so what are these elementary matrices? Okay, and elementary matrix is that which is obtained from unit matrix, from a unit matrix by performing some of the elementary transformations. Okay. Now, whatever we have discussed, that row operations R2 is exchanged with R3, and R2 is replaced with K times R2, then maybe for R1 plus K times R3. So these three type of operations we have seen for row operation. Similarly, we can do column operations also. So these are elementary transformations. C2 can be replaced by K times C2, then and then it is maybe C3 can be replaced by C3. So this is replacing R1 plus K times C4. So these are elementary column operations, column transformation, elementary transformations. Okay. Now, what is an elementary matrix? What is an elementary matrix? So it says if we, for example, if we take I3 is 1 0 0 0 1 0 and 0 0 1. So if we just perform some row or column operations, and then the matrix that we'll get will be called as elementary matrix. For example, R2 exchanged with R3. Okay, this event we'll call this matrix as R23. Okay. So this is equivalent to write R23. So this would be 1 0 0. So 0 0 1 and 0 1 0. Note that because of this procedure, so this column is also replaced with the other one. So this is again writing C23. So when we are doing R23, so at the same time it is becoming C23 also. That means column 2 has now become column 3. And this is column 1. Okay, so this is row 1, row 2, and row 3. So column 1, this is column 2, this is column 3. Now it has become R1, then R3, and R2. Okay. Now for a given any matrix, if we multiply this particular elementary matrix, okay, then what will happen? For example, let us suppose A is given. Let us call it 1, 2, 3, 4, 5, 6, 7, 8, and 9. So let us suppose this is given. Then we want to multiply R23 times A. Left multiplication. This is called a pre-multiplication. Pre-multiply. Or left. Left multiplication of A. So let us not introduce any new term. So we will use the textbook term. It is pre-multiplication to A. That means we will take that. So what is R2? 3, 1, 0, 0, 0, 0, 1, 0, 1, 0. And if we do this matrix multiplication, 1, 2, 3, then it becomes 4, 5, 6, 7, 8, 9. So this will give us, so if you just do this multiplication, so then 1, then it will become 2, it becomes 3. But now, since 1 is here, so this will become 7, then 8, then 9. And then it will become 4, 5, and 6. So what just happened now? Look at here. So if you just call it this is R1. So let us call it R1, R2, and then R3. This is C1, C2, and C3. So now we can see that R1 remains the same, but R3 has come up, and then R2. So if we do just only row operations, then what we do? Next step, R2 exchange with R3. So if we do this elementary row operation, elementary transformation, or if we multiply this pre-multiplication, of this elementary matrix to the given matrix, then it will give us that the rows will be exchanged. But remember, here these columns are not exchanged. You cannot see that there is this column are actually. So this is now this column C1 dash, C2 dash, and C3 dash. Okay. So simple operations are not happening. Okay. So what has just happened? This row are exchanged. Now what will happen if you do this multiplication, post multiplication a time? That means you will take it on the right hand side. Okay, so this will give us 1, 2, 3, 4, 5, 6, and then 7, 8, 9. If you do this, so 1, 0, 0, 0, 0, 1, 0, 1, 0. So what will happen now? Let us look at the terms. So for this one, 1 or 2, 1, and then it becomes 0, 0, 1. So it becomes 3.
1, 3.
So this becomes, now it is 2. Similarly, this is 4. Now it becomes 6. It becomes 5. And then this is 7. So this, okay, this is 9 and 8. So what just happened now? You can look at here. Now this is row 1 test.
C2
But,
and C3 are exchanged.
Yeah, it is row 1. Can you repeat? Row 1 test. But here, if you look at C1, this is C3, and this is C2. So if we multiply any elementary matrix on the right hand side, that is called post multiplication, then columns are actually exchanged. Okay. Now we have seen C for this elementary matrix, this is nothing but C23, R23 and C23. So that is why even if you multiply here C23, it is also same actually, R23 and C23, as you can see here. Since only 0 and 1s are here for this particular matrix, for this identity matrix, and for elementary matrix, it is just a modification, a slight modification of some this identity matrix. So if you just do, now if you recall that for a given matrix, 1, 2, 3, 4, 5, and 6, 7, 8, and 9. Okay, for this given matrix, this is a 3 by 3 matrix. So what we do here, if we multiply some 0, 1, 0, 0, 0, 1, and let us call this is A. Okay. So this is A matrix. Sorry, A matrix is given here. Then we will write here A, and then right hand side there will be another matrix 0, 0. So these are the elementary matrix. I mean, these are presently they are I3, A, I3. So they are presently identity matrix. Now, if we do some row operations, 2, 3, okay. So what happens? It is actually affected by the pre-multiplication. Okay, so row operations, row transformations. That means pre-multiplication. So that is why the left hand side matrix will change if we do the row operations. If we do column operations, column transformations, so this will become post multiplication. So the right hand side matrix will change. Now question is, if we have A is a 3 by 4 matrix, then what will happen? Then again we have seen that A will be written as I3 A times I4, because the right hand side we have to match the order of the matrix, the dimension of the matrix we have to match it. So this is a 3 by 4, A is 3 by 4, then the right hand side will be I3 by 3, then A will be 3 by 4, and another matrix will be multiplied by, so this is I4 by 4. Yeah. So these dimensions are matching now. So here it is. Okay, so that is why we have taken this matrix. So this is I3, A, I4. And for row operations, so that was working procedure. Actual reason is actually this one. So if you are doing this pre-multiplication by some elementary matrix, okay, and post-multiplication by another elementary matrix, then these rows are only changing, okay, for pre-multiplication. But if we do this post-multiplication, then the columns are changing for this particular matrix. The matrix is same. So this is A, this is kind of Q, this is P, this is kind of A. Okay. I hope this clarifies your doubt. Now, today we are going to discuss very important topic. It will come to your whatever hereafter, whatever you do, whether you do engineering problem or some mathematical problems. It does not matter if you are electrical engineer or civil engineer or any other engineer. So this particular concept is very, very important.
Sir, can you please show the previous slide?
Yes. This one?
Well, thank you, sir.
Okay. So the concept is called eigenvalue. And eigenvector. Okay. So what are those? Actually, it has there are many names for these eigenvalues and eigenvectors. The origin of this concept is actually it is from German. I think it is from German word, which means perfect values or latent values, or some other different names are there. But anyway, we don't have to bother about the other names. We just have to be careful about the concept. So it has some other names also. These are sometimes we call it eigenvalue, or it is also sometimes called characteristic value, or it will also be called as characteristic root for this eigenvalue. Okay. Why such names we'll understand after some time. So first let me tell you about the concept. Okay. So for example, if I tell you that I am giving you 100 rupees, okay, make it, for example, 3 partitions, 30, 30 and 40. Okay, and I am telling you I am giving you 100 rupees, so make it 200 by any way. You can I mean, I am not encouraging to do any kind of betting. Okay, so if some people, Mr. X, he may think that he purchase, maybe he will try his luck, lottery. So this 100 can also be like this power. Okay, it can be 1 lakh, 1 crore, if he is lucky, provided if he is lucky. If it is unlucky, then he will lose, 100 will go to 0. So that is not a wise choice. But there can be some, let us not Mr. or any kind of miss X or some Y, they may have some better plan. They can do maybe this recurring deposit. They can also do fixed deposit. They may also invest on mutual funds. Okay. So for example, for recurring, they are telling they are giving 30. For recurring deposit, they are, for fixed deposit, they are giving some 40, then this is 30, and then this is 30. Remember, I am telling about only 100 rupees. But 100 rupees is a very less amount if you want to. What happens if this is 100 million or 100 crore? Try to juxtapose the situation like in a big numbers. Okay, but if I put here some more zeros, then it will be, I mean, not very friendly to understand. So that is why we are taking some little, I mean, small numbers, and we can juxtapose the situation for large numbers. Now it has some return rate. It will give you some return, maybe for 5.5%. Fixed deposit, it has some 6.5%. Then it may have some, but the mutual fund, it will have subject to the like you have maybe you have seen the advertisement for mutual funds. It will have a risk. if the market is down, then it will have a lower, maybe it can be 6% return. So after some time, this 30, you have to make 200. So either you will double it 60. This is also become 60. Sorry, this will become 80. This has to be 80. And this has to be 60. Then only you will have 200. That means this 100 rupees will become 200. So there is a the certainty amount will be there. If you do fixed deposit and if you do this RT, this recurring deposit, if you lose the money also, then some amount will be there, at least not like this. Either you get high value or zero value. Sometimes it is called either you become hero or become zero. But here, if you do some logical choice, logical activity, then it is not going to give you zero, or it is not going to give you certain amount, certain large amount. Okay. So what we are doing actually, we are trying to scaling this 100. If you call it a x is a vector, for this is x1, x2, and x3. If this is a vector, what we are trying to make it a 2x. Okay. Now, depending on the realistic situations, this is a real situation also, but this is not recommended to purchase any lottery. This is kind of betting. Okay. If you, but you can argue that since this is 100 rupees, I have so many. So if I do 100. Then nothing wrong is there. But yet again, this will give you some kind of betting addiction, which is again not recommended. So every time we have to do a logical choice. So thus, sometimes it may be reduced depending on the situation. So 30, 40, it becomes 1 point. So 160. For example, even if this does not give you some payment, so definitely you will get 140 will be there for sure. But in order to get this 140 amount, you have to wait maybe for 10 years. But if you do this choice, maybe within 1 month, you can get this large amount. At the same time, you have the risk of losing everything. Okay. So this is a very risky choice, but here it is logical choice, but it will take some time. Okay. Now at the beginning I said that I am giving you 100 rupees, make it 200. I have not given the choice. I mean the time I have not mentioned. Okay. So if I mention like you can protect 1 year to 10 years, then you can make, depending on your choice, I mean depending on your skills that you can obtain. Now the same thing you have to make it. So take a matrix, given a matrix 1 1. Okay, if you just multiply ax, then what you will get 5, 2. So it is actually not kind of 2x. We are getting some y. 1 1 was there, so we are not able to make in terms of 2x. So we are getting another vector for this matrix. Okay. So what happens? 1, 1 is this vector. This is x, 1, 1. And if we multiply with this particular matrix, this non-zero square matrix, so we are getting another different vector. Although it is a large value, but in a different direction. But there are some particular, if we choose this x and if we multiply with the same matrix, then we can see this becomes 8 and 4. This is 4 times x. So what just happened now? This x vector is just becoming scaled 4 times. And we can see that this particular matrix, x is a matrix, and here we are getting 4x. So it keeps the direction same and it changes the value also of the vector. The magnitude is also changed. In this case, what we are having? We are getting a different vector, not in the same direction. These two vectors are actually different. They have different directions and different magnitudes also. Our aim is to get scaled in the same direction. When we call it scaling, if we magnify it, this vector is magnified in the same direction, then we call it a scaling. It can also be in a situation, for example, half x. It can be half x also. So in that case, this vector will be reduced. In that case, if you, for example, this is the matrix. This is our x vector. We can have a different situation so that we get half x. This is also called a scaling, whether it is increased or decreased, but in the same direction, in the same line. Okay. It can also be of this form. I mean, in the negative direction also. This is also scaling. So this can be like minus half x or minus 4x. So this, at this case, this will be like this. Okay. Now, if you want to scale whatever the quantity that you have, maybe if you have a small size of any round shape or anything else, okay, if you want to scale it, what happens? These directions, all the direction, you have to keep them same and try to scale it. If you think about in the vector terms, this is also scaling. Either you magnify it or you can shrink it. Okay. So this is also becoming from here, from a small shape, you're trying to make it, or vice versa. From a big shape, you're trying to shrink it. So make it small. That this is also scaling function. I mean, scaling that is happening here. Either in this case, we have seen only one vector here also. Now, if you look at this situation in a, what is it called? Yeah. In your kitchen also, you if you look at your kitchen, you will see this example. You know what is roti? Roti, chapati, or anything. First, you will look at your, when somebody is cooking, they are preparing, the small size of amount will be there. And then after some compression and then after putting pressures, it will be large. So that this function, this small quantity is actually magnified in all directions, keeping all the vectors within it in the same direction. So if you think about the vectors that is available inside all the vectors, they are keeping same in that direction. All the vectors are keeping their direction same, and they are just getting magnified. Okay. So that is also, you can think of this situation. Now, if you have understood this geometry, then you have understood the concept of eigenvalues and eigenvectors. So the formal definition of eigenvalues and eigenvectors. So what is it? If we have a matrix, a square matrix, A is n by n matrix. If we have some real or complex number, that is lambda, okay, and there is some non-zero vector x, okay. So if it satisfies this equation, ax equals to lambda x. See, this is a very simple equation, just ax equals to lambda x. But you will be, in fact, this will be most important equation in linear algebra or matrix theory. Very simple equation, but very important, very powerful equation. So if it satisfies these conditions, x should be non-zero. For a non-zero vector, if we have this equation satisfied, then we call this lambda as the eigenvalue, and this particular vector will be called as eigenvector. So whenever you talk about eigenvalue, you will always have to think that they come together. It is like they are come the twin brother or twin siblings. Okay. Eigenvalue and eigenvectors. They cannot be defined independently. They all the time you have to talk about the eigenvalue and eigenvector. Okay, they are not independent quantities. Every time they come like a package. If you talk about eigenvalue, you have to talk about the eigenvectors. Okay. So if you just simplify this equation, then ax equals to, if you take this lambda x on the left hand side, then it will satisfy. Remember, this 0 is actually geomatrix. You're talking about matrix. Okay. Now we have seen that this matrix is non-zero. We are assuming for a non-zero matrix x, if we have this kind of equation, then if you take this determinant of this side, then this will become actually 0. So determinant of this particular matrix A minus lambda I is an identity matrix of the same order. Then this lambda is an eigenvalue of this matrix. So remember what is happening here. Ax is lambda x. So this lambda, this x matrix, x vector is getting scaled by this matrix, and the coefficient of scaling is becoming this lambda. Okay. So in this situation, what we say, that lambda is an eigenvalue of A if and only if the determinant of A minus lambda I equals to 0. Okay. And this here is a note. This called the characteristic equation of A. If the matrix is n by n matrix, then this equation will have n roots. Whether they are similar or different, that is a different matter, but it will have at least, not at least, at most n roots. Okay. Now here it is called characteristic values. These eigenvalues are called characteristic values because they are actually derived from the characteristic equation. So that is why we call it characteristic values or characteristic roots. Now it will be clear if we see one example. So if we have a matrix, let us take one example, one simple example. For example, 4 minus 5. The question is how to find eigenvalues and the corresponding eigenvectors. So let us see one example. 4, 5, so 2 minus 3. Okay. Then what will be the characteristic equation? So determinant of a minus lambda I equals to 0. So here let us take I equals to same order. So this is 1, 0, 0, 1. Okay. Now lambda is a real or complex number. That we will find out whether it is a real or complex number. Okay. So let us, so lambda I becomes lambda minus lambda 0, 0 lambda. Okay. Now what happens? A minus lambda I. What is it? So 4 minus lambda minus 5, 2 minus 3 minus lambda. Now if you take the determinant, okay, the determinant becomes 0. So this is our determinant, or you can write it in this form also, 1 minus lambda I, same. So this is our characteristic equation for this particular matrix. So if you just expand this, what will happen? So 4 times minus 3, so minus 12. 4 times minus lambda, so minus 4 lambda. So lambda times minus 3, minus lambda times minus 3. So this becomes 3 lambda. And then minus lambda times minus lambda, so plus lambda square. And then 2 times minus 5, so this is minus 10. And since we are evaluating the determinant, so this becomes minus and minus, it becomes plus 10. Okay. Now if you just simplify, it becomes lambda square minus 4 lambda and 3 lambda. So minus 4 lambda and plus 3 lambda. So it becomes minus lambda. Similarly, it becomes minus 12 plus 10. So this is 2. So here it is 0. So if you just try to find out, the characteristic equation now becomes lambda square minus lambda minus 2 becomes 0. So this is kind of ax square plus bx plus c equals to 0. So quadratic equation. So what will be the lambda? So minus b.
So lambda will be 2 and minus 1, sir.
Yes, that is right.
Sir, we can directly factorize it, sir, actually. Like
Yes,
lambda
yes,
minus 2 into lambda plus 1 is equal to 0.
Yeah, if you can do the factorization, that is also called factorization. So here it will be lambda plus 1 and lambda minus 2. It becomes 0. Since this is a simple equation, so you can directly find lambda equals to minus 1 and 2. That is one way approach. So another approach. So here it is minus b plus minus root over b square minus 4ac, right? Divided by 2a. So in this case, what we have? Minus 1, minus 1. So 1 minus 1 square plus, sorry, minus 4 times 4ac. A is 1 and c is minus 2. Okay. I am doing this for if we do not have a simple equation. Sometimes we may have some different equation. So that is why we have to be prepared for all conditions. Okay. So here it is lambda equals to 1 plus minus. So 1 plus 8 divided by 2. So you will get here 1 plus minus 3 by 2. Or you can write just 4 by 2. And here it is minus 2 by 2. So lambda becomes either 2 or 1. Okay. So these are the eigenvalues. Eigenvalues of A is minus 1 and 2. Okay. Now, if you remember the definition, Ax equals to lambda x, where x is this vector x1 and x2 for this particular 2 by 2 matrix. Okay. Then now we have lambda equals to minus 1 and 2. So lambda is called eigenvalue corresponding to the vector x if it satisfies this equation. So for this lambda equals to minus 1, for this eigenvalue, the equation will become Ax equals to minus 1 into x. So here what we'll have, if you also recall what we had from here, we have seen that A minus lambda times I, x equals to 0. So you can directly write it here also. A minus lambda times I equals to x equals to 0. So here, if you just put A equals to 4 minus 5, 2 minus 3, then lambda I, here lambda is minus 1. So let us write minus 1, then 1, 0, 0, 1. And this is x equals to 0. x1 and x2, they are unknowns.
Hello, sir.
Yes, tell me.
Sir, sir, in this equation, why can't lambda be just the matrix A, sir, other than this minus 1 and 2? Obviously, these are satisfied, but why can't it be just directly
Tell me.
A? Sir, why can't lambda be just directly the matrix A, like in this equation?
No. Why? You have to satisfy
will be
all these things.
Okay.
You are telling what is a matrix? This is a real number, and you are talking about this is equal to I, a matrix, which is not correct. In that case, I will ask you, what is a matrix?
Oh, yes, sir. Okay, sir. I didn't see the det for that. It's A minus lambda. Det of is. Okay, sir. Okay, sir. Okay.
You're telling a real number is equal to a matrix. So that's completely, misunderstanding. Okay. So you have to satisfy all this equation. Say this equation is very simple. Ax equals to lambda x. No other equation is more simple like this. But its importance you will understand over the years. Coming years, you will understand that how this scaling function is actually able. So if you work in shape geometry, shape optimization, then you will use this concept, this of what is it, eigenvalue and eigenvectors. Like I said, that if you just look at your kitchen, this shape optimization are done in your kitchen. You can find it. These vectors, all the vectors will keep their direction, and if the direction are not matched, then you will say that this roti will not be round. It can be triangle and some other shape will be there. when this eigenvalues are not eigenvectors are not actually properly handled.
Sir.
Just tell me. So let us just try to find out how to get this vector. Any doubt? Venkata, yeah, tell me.
Sir, for deriving characteristic equation, we have taken ax minus lambda x is equal to 0, na sir.
Yes, yes.
From that, we had derived a minus lambda I into x is equal to 0, sir.
Yeah, yes.
From that, how can we derive determinant of a minus lambda is equal to 0, sir?
No, this is, you are not deriving. We are telling this if, see here, this note, if lambda is an eigenvalue, okay, of the matrix A, then this determinant of A minus lambda I will be 0. Or if this determinant is 0, then this will happen. This lambda is an eigenvalue. This is the guarantee. This is guarantee.
Okay, sir.
Okay. This remark is giving you the guarantee that lambda is an eigenvalue of A if this determinant is 0. In other sense, if this determinant is a 0, then lambda will be an eigenvalue of A.
Or, sir, or we can apply det on both sides for a minus lambda I into x is equal to 0. Then we might get det of AB is equal to det A into det B.
No, not like that. You have to follow this definition. Determinant of A minus lambda I is actually characteristic equation. So if you want to find out the characteristic values, that means the eigenvalues, you have to satisfy this equation.
Make det of A minus lambda is 0. Okay, sir.
Okay, this is our standard procedure. Make this 0, find out the value of lambda. This lambda will be called characteristic equation, characteristic value or eigenvalue.
Okay, sir.
Now we want to find out the corresponding eigenvector. Okay, so this x is nothing but, let us write it in the x1 and x2 form. So this is 4. So minus 1, and here it is also minus 1. So this becomes plus. Okay, so 4 plus 1. So this becomes 5. So minus 5 plus 0. So this becomes minus 5. So here it is 2 plus 0. This is 2. Here it is minus 3. And here it is plus 1. So this becomes minus 2. Okay. The system of equations now become x1 and x2. So this becomes 0 and 0. Right hand side 0, that means it is a 0 vector or 0 row, 0 column vector. Right? Your idea should be clear, crystal clear, that this is what we are talking. This 0 means this is a 0 vector, 0 matrix of order. You have to match the order also. Okay. Now this is a simple equation. So it becomes 5. Either this is the system becomes, what is the rank of this matrix? Of this matrix? Or if you can just try to find the augmented.
1.
Augmented matrix AB, it becomes 5 minus 5, 2 minus 2, 0, 0. Okay. Then, yeah, so this will become another matrix is called. So this augmented matrix, here it is. 5 minus 5, 2 minus 2, 0, 0. So if you reduce it, the system becomes 1 minus 1, 0, 0, So 0, 0. Row operations. Okay. And this will give us the system of equations. The system becomes reduces to x1 minus x2 becomes 0. So x1 equals to x2. Okay. So for simplicity, we assume x2 equals to 1, then x1 becomes 1. So the vector that we want to find out, x1 and x2, corresponding to lambda equals to minus 1. So this is becoming 1 and 1. Now if you try to look at the matrix, okay, so for A, this is 2 minus 5 and then 3. If you multiply this vector 1, 1, okay, then what you will get? Definitely it is going to be of this form. Since we have found this is a eigenvector, this is an eigenvector corresponding to the lambda value, this one. So this is satisfying. So you can also verify Ax equals to minus, it is 1x. So minus 1 is the lambda value here. Now, how about the other eigenvector? That was for lambda equals to 2. So A minus 2i. Okay. You can directly write. So this is right hand side will become 0. So let us write down the system of matrix. So this will actually become the right hand side, the augmented matrix. Let us write the augmented AB. Okay, augmented matrix. So here this is 4 minus 5, 2 minus 3. Here it is 2. 2 times 1, 0, 0, 1. Okay, and we are taking the 0, 0 augmented matrix. So this becomes 4 minus 2. So this is 2. Minus 5, 0. Minus 5 minus 0. So minus 5. Then 2 minus 0. So this is 2. So minus 3 and minus 2. So this is minus 5. So the system becomes again same equation. So this, if you do the row operation, so the system reduces to 2x1 minus 5x2 equals to 0. So if you just take 2x1 equals to 5x2, so here you will get, we'll try to find out integer numbers. Okay, so x1 equals to 5 by 2 x2. So these are the relation between x1 and x2. So take x2 equals to 2 and then x1 will become 5. So this is also another eigenvector. So it is 5 and 2. Now it can be asked, the question remains that in the previous example you have taken x2 equals to 1. Now why you are taking x2 equals to 2 here? Even if you take x2 equals to 1 here also, then it will give you x1 equals to 5 by 2. Okay, in that case, the matrix, the eigenvector will become, so 5 by 2 and 1. it is again, if you just do some row operation for this particular, so it is equivalent to just one step we can get it. If you just multiply by 2 some row operations or some column operations, okay, elementary column operations, then you will get 5,2. We'll try to keep them as integers, not fractional numbers. If it is not possible, then we have to keep it as fractional as it is. Otherwise, by suitable choice of these values, we will get the other value. So these were unknown. Now, if you try to verify this matrix, as 4 minus 5, then 2 minus 3 times, if you multiply by 5 and 2, then definitely you are going to get this value, 2 times 5 by 2. Okay, so you can see that this particular vector 5 comma 2 is actually scaled 2 times by the matrix on the left hand side A. It is given. But if you look at the other situation, here it is, this matrix A, here it is, A matrix is 4 minus 5, 2 minus 3. If you look at this 1 comma 1 matrix, which is actually minus 1 times 1 comma 1. So it is also getting scaled, but its direction is going to change. Okay, so this is how we try to find out for 2 by 2 matrix. We can find out the what is it called, eigenvalue and eigenvectors for 2 by 2 matrix. Now there are some more examples. If we have a 3 by 3 matrix, the procedure is same. I have included those topics. Yeah, so all these stories that I have told so far. Yeah, so here it is. All these stories are done. Yeah, so this is example 2. If we have a 3 by 3 matrix, then we'll have to take I3 and A minus lambda I, we make it 0 and try to find out the values. Lambdas are, so here the eigenvalues are 0, 3 and minus 4. So you have to find out eigenvectors now. So take the augmented matrix. The right hand side will always be 0 because we are trying to solve this a homogeneous system. Okay, so we will do the row operations and try to find out the try to reduce the system of equations, system of linear equations, and it becomes reduces to the here. So depending on the situation, we have to take t equals to, so t is a parameter. Okay, here we have to understand the which are the basic variables and which are the non-basic variable or free variable. So here in this case, x1, x2 and x3. So here x3 is a free variable. There is no pivot element here in this case. There is no pivot element. So here x3 is the free variable, and x1 and x2 are independent. So that is why we have to take these solutions as of this form. Okay, x3 13. So x1 becomes this is an eigenvector corresponding to the value 0. So 0 can also be an eigenvalue because we have said ax equals to lambda x. Here we are not telling whether it is 0 or non-zero, but what we are mentioning that this vector should be non-zero. Eigenvector, 0 vector cannot be eigenvector. So make a note. But lambda can be 0 also. So these are the idea. So similarly, if you want to find out the eigenvector corresponding to this lambda equals to 3, so you will get here eigenvector this one. Similarly, if you want to find out some other vectors also, sorry, this is lambda equals to 4. minus 4, and for x2 becomes this one. So all three vectors are obtained. Now we have to find out, sorry, these are from your practice problem. Try to find out the eigenvalues and corresponding eigenvectors. So I'll stop here with the concept of eigenvalues and eigenvectors. In the next class, we will do some more examples about this and try to look at some other aspects of eigenvectors and eigenvalues. So if you have any doubt, you can, of course, ask me. Already it is 9:10.
Eigenvectors will be only of